I'll do a short presentation, and then we'll jump into 2 pieces of code. The first piece of code that we're going to look at is going to be about how to use Llama Index with a vector store, and then that builds into the second piece of code that we're going to look at, which is going to be a notebook on how to do multi-document querying, or how to build a multi-document query engine using Llama Index. And yeah, so I'll just get started. So today we're talking about retrieval augmented generation at scale. My name is Yujian. I'm a developer advocate at Zillow right now. If you scan that QR code there, that'll take you to my LinkedIn. That'll take you to my LinkedIn. Whoever is like really noisy, please mute your mic. Okay, so this presentation is going to be pretty quick. I'm going to just start with a bit of a primer on large language models. I don't really know how to work teams, but I will stop between sections to let people ask like a couple questions. And if there's no questions, then I'm just going to move in between the sections. So first, we're going to talk about large language models. So we're just going to go back and we'll talk about machine learning in general. So neural networks are the basis of large language models, and this is the picture of a very basic kind of neural network. This is like essentially the smallest kind of deep neural network that you can make with like a hidden limit in the middle. And then what it does is it takes some inputs, it does some math, and then it outputs something. And this output is typically a prediction or a classification. As we start working with text, we kind of move to this model called recurrent neural networks. Essentially, what this allows you to do is this allows you to input a sequence or a series of like an input and series basically, and it keeps track of the last like t steps. So the recurrence relation is really something like, hey, I'm going to keep track of this information for the next 5 rounds, basically. So that's how you create this time series, and that's how you get ability to have a sequence input. One of the problems with recurrent neural networks is that they lack the ability to keep track of context over a long time, because essentially the length of the input is the length of your context. And I'm sure you guys have heard the word context or context window many, many times. Context, whatever. That indicates like the input size here in the transformer. So for example, this transformer architecture was basically made to solve this sequence to sequence transduction issue that recurrent neural networks have. Their input sequence and output sequence have to basically be the same. And so transformers allow you to take an input such as 100K tokens, and then you can transcribe that into a hidden state. You can encode that, transform that into a hidden state, which you can then combine with additional input or not. The additional input is optional, and this is typically what the additional input is in the form of a matrix, and is typically what people call self-attention. And if you've heard this term self-attention, that's kind of how it's done. It's done by sending a matrix to the decoder. The hidden state is also a matrix. The decoder basically just takes these matrices and gives you an output, which in the case of GPT, that output is the next word, right? So what GPT does is GPT takes the transformer model, which solves the sequence transduction problem, and it uses the decoder only architecture to change the problem statement from, hey, I'm going to give you this sequence and I want you to output a sequence, to, hey, I'm going to give you this hidden state and I want you to tell me what the next word is. So that's what GPT does, and this is a primer on large language models. This is basically all you need to know about large language models for this presentation. Are there any questions that I can answer at this moment? Okay, I don't see any questions popping in the chat. I don't know if they're just taking a while to type or not, but I'm going to go on. Okay, so the next thing we're going to talk about is vector databases and why you should use them with large language models. So we're here to talk about RAG mostly, so retrieval augmented generation. for us at Zillis, we picture this with 3 different components to the stack that kind of makes it look like a computer. And the 3 components that we think about are a ChatGPT like LLM, so something that allows you to interact with this application in a chatbot form. And then a vector database. This is essentially your knowledge base. So if you have your own data, which most enterprises have their own data, then this is your knowledge base. This is your knowledge store, whatever, single source of truth, etc., for the large language model. And then something like prompt as code, which is what we're going to be doing, forming with Llama Index today. But the example that I have here is Haystack. And this is your interface. This is your code. So if you think of a computer, is that what I have in the next stack? No, that's not. Okay. If you think of a computer, you can think computers, they have like a CPU. That's your your large language model. That's your compute power. That's your processing. And then you have like a hard drive, and that's your vector database. That's your storage. That's basically your ROM. And then prompt as code. This is the way that the different parts of your computer talk to each other. Okay, so how does RAG work? Retrieval augmented generation starts with you having some sort of knowledge base, you having some sort of documents. And what you do with your documents is you pass them into a deep learning model. This is called your embedding model, and you chop off the last layer here. So this last layer here is actually not supposed to be here. Like that. But with RAG, we just want the encoding. We just want the vector embedding, the example. So we don't need the last layer. We want the second to last layer's outputs. And that is a vector. And then you store the vector in something like Milvus or Zillis. And that is essentially the first step to building your knowledge base, right? Building this V part of your CVP stack. You get all your vectors, you encode them with an embedding model, and then you store them in a vector database. From there, so that's steps 1 and 2, right? You have your unstructured data, this is your knowledge base, then you get your vectors through some sort of model. This is kind of a weird diagram, but hey. Then you get a vector embeddings, and you store that in your vector database. So that's steps 1 and 2. So now the rest of similarity search is the query. So you as the user can come in with some sort of data, some sort of unstructured data, or with natural language, and once again, same embeddings model, so you get the same vectors. You can actually use a different embeddings model here, and typically the only reason you would do that is if you're trying to measure the differences between what your models have learned, and then this is a process called graceful degradation. But anyway, if you're doing RAG, what you want to do is you want to use the same model. Unless you're doing observability or testing. And then you basically just get that vector and you put it into the vector database, and it runs some sort of, what's it called? Approximate nearest neighbors search. Oh, it's written right there. Approximate nearest neighbors search, and that gives you the closest neighbors inside of the vector database to your query. So that gives you the sentences or paragraphs that are the most semantically similar to the sentences or paragraphs that you have just put in, or if you're doing images, the images that you have put in. Okay, so what is semantic similarity? This is something that I feel often makes sense to explain to most audiences. And semantic similarity is basically saying like, hey, we can measure how similar some words are using numbers. And so what it allows you to do is it allows you to do math on things that are not typically represented to us as numbers. So with this example, what I'm going to show you is we're going to use these 2-dimensional vectors of queen, king, woman, and man to show that queen minus woman plus man is equal to king in terms of semantic similarity. So the first things I want to draw your attention to here are these first numbers in these axes, and sorry, the numbers in the first axes. So you'll see that queen and woman are both 0.3, and king and man are both 0.5. And what this indicates is that based on the embedding model, these 2 words are the same meaning along this dimension. And then I also want you to draw your attention to this difference between the the y values here, the second dimension here. And notice that these two have the same difference along the second dimension. And what that indicates is that these words have similar relationships. So if we start with the word queen, we have 0.3, 0.9, and we subtract the word woman, which is 0.3, 0.4, we get 0.0, 0.5, which I suspect probably relates to something like the word royal. And if we add the word man, then we have 0.0, 0.5 plus 0.5, 0.2, and we have 0.5, 0.7, which is the equivalent of king. So once again, all that you really need to take away from this is that vector embeddings allow us to do math on words or images or things that are not traditionally numbers. This is what a vector database, well, this is what Milvus's architecture looks like. This is not what every vector database architecture looks like. Essentially, what I want to point out here is, let's see. So there's a separation of concerns. So Milvus is particularly good at scale. There are over 50 projects that use Milvus in production with over 1 billion vectors. And the reason that Milvus is used at scale is because when Milvus was first built with Milvus 1.0 and was released, one of the things that we saw as a high demand, as something in high demand, was the ability to scale to 1 billion vectors, basically. A lot of companies such as, like eBay or Walmart or some of these other like big tech companies that have a lot of products and a lot of data they need to be able to work with tons and tons of data at scale. And so we tore down Milvus 1.0. So Milvus 1.0 got scrapped and turned into Milvus 2.0, which includes some very, very cool features such as like the separation of concerns here. Because, for example, with search, and this is not just vector databases, but databases in general, right? You have an indexing, which creates how your data is accessed. Then you have data ingestion, that's the data node, which takes the data and puts it into your database. And then you have a query node, which is what you use at runtime when you want to know what's in your database, you do the querying. And these are all, if you think about it, these are all like completely separate processes that they can run in parallel, but they don't need to be running at the same load. For example, if you're ingesting a large amount of data, it does not mean that you need to be querying a large amount of data at that time. So and vice versa, if you're querying for a large amount of data, or if you're doing a large amount of queries, then you don't need to scale up your data ingestion. And so we separated these into different nodes so that Milvus is highly scalable in multiple directions. And then the other thing I think is really interesting is as you build your vector database, because that means I need to remake the way that I access the data. And the answer that Milvus has to that is actually no, because what we do is we create indices, and we create an index on a 512 megabyte segment. So every time you put 512 megabytes of data into Milvus, it gets sealed off to a logical segment, not a logical partition. There are also partitions. Those are a different thing. We can talk about that later. That's like a deep dive kind of thing. But it gets put off into a segment. They're 512 megabytes. And then an index is created over that segment. And so from there, every time you add data, it is simply adding a new segment to query if it's, or adding to the growing segment to create the index over. And what happens if you delete data? We soft delete it from the database. I think that hard delete is implemented in Milvus, but right now we just soft delete everything. And so because the data segments are created in that manner, it's also something that lends itself to scalability because it is much, much more efficient to query 512 megabyte segments simultaneously than it is to query 100 gigabytes serially. Okay, so that's pretty much all there is on the vector database section. Let's see. Oh, questions. How's vector data stored in Milvus? Can you please give more info about it? Vector data is stored actually, you know what? I have I have like it's like stored. You know what? I'll just show you my. I don't know if you guys can see this right now actually, but I can just show you what it looks like. And so, okay, cool. Yeah, this is what vector data looks like when it's stored. It's like it's like your metadata, your schema, and then like a long ass embedding. This is your vector. Cool. Okay. Okay, cool. That looks like that was all the questions here. Someone's typing, so I will answer this in a second, but I'm just going to move on and I'm going to talk about this. We'll talk about this in a second. No. Actually, we'll talk about this first. So this is the architecture of the overall application that we're going to build. Is everybody planning to do a code along, or would you prefer me to just give you guys the code and you can just like listen to me talk about how it works? Does anybody have opinions on this?
Are you asking kind of for a walkthrough versus the hands-on?
Yeah. So I found that not everybody like I found like it's not everybody wants to like code along as I'm doing it, or as I walk through the code, and some people do. And based on what people want to do, I will take different approaches to basically going through the code. And so that's why I'm asking.
Perfect. Maybe folks could raise their hand if they want to do like code with you. Does that sound good?
Looks like people want to do a code along. Okay, cool. So code along is great. All you really need to do is have a, get your VS Code or whatever your IDE is out. If you're not using VS Code, I'm sorry. And then I will have all the pip installs. So I'm actually just going to put the pip installs here so that you can go ahead and get them in there. And then I will walk you through the architecture, and then we'll walk through the code. So this is the architecture of the final app. The first thing we're going to create is we're just going to link LLM index to a vector store so you can see how it works. And then we're going to create something much, much more complicated. This is actually a very, very fun, very interesting kind of project. So essentially what it does is this allows you to take a query such as tell me about the airports in Seattle and Houston, and it allows you to decompose that into two parts such as tell me about the airports in Seattle, tell me about the airports in Houston. And then what it does is it routes that. So that's this part. So first you're giving tell me about Seattle and Houston, airports in Houston, and then query decompose, and it goes to the LLM and it decomposes that. So it actually kind of goes back like this. And it decomposes it and it says, hey, tell me about Seattle, tell me about Houston. And then that goes here where you have a multiple list of documents. And some of these documents the first routing is done with keywords. And so these documents have things like, this is an article about Seattle. This is an article about Houston. Very, very basic for this case. Obviously, in a real world environment, you would probably want something much, much, more that makes much more sense. You probably maybe want some commas with your keywords. But for this basic example, it's just going to contain the title of the city. And then those keywords will tell you which vector stores to query for the semantic meaning, and then they'll return it, and then they'll return it to the large language model to put together to give back to you to say, hey, like this is the airport in Seattle, this is the airport in Houston, this is how they differ and how they're similar. So the first thing we're going to walk through is we're going to walk through this. We can't see the collab. Oh, okay. Anyway, that's because the collab is not available. I'm not looking at the collab right now. In fact, I'm also not going to go through the collab. I'm just going to go through. Well, is this this one have the? Oh, this one has the outputs on it. Okay, I'll go through the collab on this one. But this QR code here should get you the collab notebook. I guess I will just walk through the codes. It looks like you guys want me to kind of explain the code concepts as we go. So this gives you the Colab, nope. Did everybody get a chance to scan this? Everybody's good? Everybody has the link? Oh, actually, you know what? I can send the link in the chat. Oh yeah, I forgot about that. Okay. So here's the link. So for this one, this is basic, we're going to packages. These are used for Milvus. This is Llama Index. This is for OpenAI, and this is for managing your environment variables. So this is just the imports. This is unimportant. This is loading environment variables. So this is the Milvus server, so you can run it locally. I will note that I don't know if Milvus runs on Colab right now because it was broken a little while ago. I think within the last couple weeks due to some updates. And I haven't checked it since because I typically run it locally. From Llama Index, you're going to want Milvus Vector Store from their vector stores, and then you're going to want GPT Vector Index, which is the same as Simple Vector Index, and storage context. This allows you to pass the vector store, Milvus Vector Store, into the vector store index, and then you're going to want a directory reader that will read some data. The first thing I do here is I load my OpenAI key because we need to access GPT, and then I start Milvus. And as you can see, this is from a while ago because this is 2.2.6, and Milvus is now on 2.3. Or maybe that actually gets released this week. Zillus is on Milvus 2.3 anyway. The way I connect to Milvus is I create a vector store and I connect to the host and the port. So this is the same way you would connect to a SQL database or a NoSQL database or any database that you're running locally, really. There's no magic tricks here. It's just host port. And then you read your documents in. And so in this case, I had some data. And actually, I should probably find where that data is. Is it not at the top of this? No, it's not. Okay. The data is here. And this is where you can get the data. I'll put this here. Oh, wait, what? Oh, is this one not? Do I not have this one shared for everybody? Oh, it's not. Oh, whoops. How do I do this? Link. Okay, there you go. Okay, cool. Yes, okay. So now you guys have the GitHub link as well? Yes, okay, so the data link as well, so you can go do this later if you would like. Make sure that you're in the right directory, right? So once you have the documents loaded up, you create a storage using the documents in the vector store. So you basically say, hey, the vector store is what we're going to use to store our data whenever I pass this storage context. And you can also see that I misspelled storage context here, and I put 2 R's, and I never had to correct it because all I did was press tab to finish the variable name. And then you can create your index. So we're creating a vector store index, and basically what this means is, like I was saying earlier with this indexing part, one of the ways you access your data is creating this index. And then we just say we're going to create an index from the documents we just read. And this is a very specific type of variable that's like, and this is like, it's just like variable type that's specific to Llama Index. I don't really like it, to be honest, but this is just what they have done, and they're, one of the few frameworks to do this. And then you just pass the source context saying, hey, we're going to store this in the vector store that we created earlier, which is the Milvus vector store that connects to your local instance. And then we create a query engine by calling as query engine on the index. And essentially what this means is that whenever we ask this question, whenever we say, hey, like, what did the author do growing up? What we're actually going to do is we're going to use the LLM to get the embeddings to query the vector store. So we say, hey, what did the author do growing up? And then, we're also going to use the LLM to structure it. So what did the author do growing up? Present, print, respond. him a TRS microcomputer. So this is about Paul Graham. He's like a pretty famous startup guy. So yeah, this is the first one, and then the second one is much more interesting. I'm going to go back to this because I'm going to reference this as I talk through this. So for this one, the difference is we need NLTK and we need LangChain. NLTK is a, how do I say this? It's a like a natural language processing package. It's older than the large language model stuff. It's been around for a while. And then LangChain, you guys probably know LangChain. It's like the chain. It's like the parrot in the chain. This is how we access OpenAI. You actually don't need LangChain for this example, but I threw it in here because I thought it would be fun. Okay. You also need PUNKT, punct, which is punctuation. Why is it called punct? I don't know. But you need to download both of those, and that's because the newer version of Llama Index uses punct, and I just haven't uploaded my corrected version yet. And this stuff right here is basically because NLTK has a bunch of really annoying SSL errors, and you just don't want to deal with it. Okay, so what are we going to import this time? We're going to start by importing the vector store index and the keyword index, right? So if we go back here, this is the keyword index, this is the vector store. We're going to read a directory in again. We're going to use this thing called LLM predictor. Basically, this says this is how we access the query decomposer. And then we're going to give it a service context, which is how we pass in the query decomposer, and the storage context, which is how we pass in Milvus. And from LangChain, we're going to use OpenAI chat, which is now deprecated. As you can tell, I created this a couple months ago, and now everything is like a completely different version because these are like super new technologies. Once again, same thing, getting OpenAI API key, and then we're going to get the Milvus vector store. We're going to start Milvus. This is the exact same thing that we did before. There's no tricks here, host, port, same as connecting to a regular database. You can tell I created this one a little bit after the other one because I'm at v2.2.8 and not v2.2.6. The wiki titles, we're going to just basically, these are like Wikipedia article titles. Toronto, Seattle, San Francisco, Chicago, Boston, Washington, D.C., Cambridge, Massachusetts, Houston, just random places basically. And then this is just, we're just scraping Wikipedia here. There's nothing important that you guys have to know about this. You can just read through this yourself. This is just scraping Wikipedia. This is the important part. This is the part that's, interesting in terms of the indexing stuff. So we start by loading up, by creating, we're going to create 4 dictionaries, but we start by creating one. And we're going to create this one dictionary, which basically maps the wiki title, that's these words here, to the actual files that were scraped. So this is where the wiki, this is the title of the city to the data. And now we're going to create some contexts. I should have put all 3 of these in the same block, but I didn't. So first we're going to get an LLM. I don't know why it's called LLM predictor, but basically what we do here is we use LangChain to pass in a large language model from OpenAI. Then we're going to use a service context, which tells us that now our whenever we use this service context, we're going to use this LLM that we just passed in. Yes, there's a lot of references here. And now we do a storage context, which we did before, which we're going to do the exact same thing. We're just going to say whenever we store anything with this storage context, use this vector store. Now we're going to create 2 more indexes. So what we're going to do here is we're going to, or 2 more dictionaries, sorry. What we're going to do here is we're going to map the title of the city to a vector store index created from the documents of a city, right? So this is earlier we mapped the documents of the city to the title of the city. Now we're going to map the title of the city to a vector store created on those documents using this storage context and this service context. And then we are going to create the keyword index. So this like string is what goes into these doc1, doc2, docn keywords here. So you can see that I clearly did not make a very, very keyword oriented example, but essentially what you can do here is just put all the keywords that you want that are connected to this. Now there are some caveats to that. All correspond to the same keyword. You're gonna have to figure out how to deal with that. I'm actually thinking of working on something which like maps a vector store to a vector store, and I think that'll be fun. Okay, so these two dictionaries are basically mapping the name of the city to the vector store index, and then the name of the city to the keywords that you want for it. Now we're going to import a composable graph. We should have imported this at the beginning, but I didn't. And essentially what this does is this creates a graph, which it starts with the table index, and then it takes in the list of these values, these GPT store indexes, and it takes in the list of these values. And then the max keywords that you allow per chunk for this is going to be 50. This is just like the keywords that are allowed in the keyword index, basically, or are to search the graph. So yeah, so this basically maps this keyword index onto these things. And now we're going to create the decomposer. So at the beginning, we talked about this query decomposer, and that's what this is. Basically, we just say, hey, our transformation, we're going to use this predictor, or this large language model that we got up here. And then we're also going to create the transform custom query engine. So this is where you're basically creating a custom routing of your query or a custom mapping of your query. And this is where things get fun. This is the last dictionary that we create. And I'm going to stop here to see if anybody wants me to repeat what I just talked about in these three blocks, or what I just talked about up until starting from this, to repeat the last few blocks about the indexes we created and what we're about to do. Anybody want me to repeat that? Okay, no repeats then. No takebacks. So for the index in city indices, this is the dictionary that we created up here. So for all of these vector store indexes, we're going to use them as query engines, which means that now we can search along this line here, basically. And we're also going to pass some extra information for them. We're going to say, hey, like, this index structure here, this is what's gonna, we're just passing, this is some extra information, and this is a searchable line is what we have so far. And then we say, okay, now we're gonna transform this query engine, this searchable line, and we're gonna transform it, we're gonna add the decomposer, and we're gonna add the extra info. So now we know that these keywords map to a searchable vector store that we mapped them to earlier, and that they use a query decomposer. Okay? So that's what we got so far, and now we say the index, whatever the index ID is, we're just going to use. And from there, we're going to create another index in here. So we're going to go to the graph that we made up here, and we're basically going to start it at the root of this graph, right? The root index, we're using that as a query engine, and we're just telling it how we're going to retrieve it. So all we're really doing here is we're saying this is like the basic way you interact with it. Simple tree summarize, which basically means we're treating it as if it's like a tree. And And then the service context is saying like, hey, let's use this LLM that we had above. And then finally, to get everything, we have this last dictionary here. We pass this dictionary into the graph as the query engine, which means that the graph will now start its queries at the index ID of the index of the root node instead of the root. And it will use these custom routes in order to route its queries. And so when you ask it to compare and contrast the airports in Seattle, Houston, and Toronto, it asks some questions, and then it gives you this answer. Seattle has one major airport called Seattle-Tacoma International Airport, while Houston has two major airports called George Bush International Airport and William P. Bobby Airport, as well as the third municipal airport called Ellington Airport. Toronto's busiest airport is called Toronto Pearson International Airport and is located on the city's western boundary with Mississauga, et cetera, et cetera, et cetera. So that's basically what this does. And then this next block of code here basically shows what you do if you don't use the decomposer. Everything's basically the same except I didn't use the decomposer up here. And then it just says compare and contrast. Compare and contrast here. And it says we don't have enough information. So yeah, that's basically how you go through this. I realize that this is actually, typically when I give this presentation, it comes out as a pretty complex presentation. There's a surprisingly small amount of people asking for repeats or questions. So I don't know if I went too fast or if this was not sufficiently in depth. But yeah, that's pretty much it to it. So I will open the floor for questions now, I guess. Thanks, John. Oh, there are two Johns in here. Wow.
I have a question for you, Yujian.
Yeah.
Yeah, so it's really generic. Like if say I come up with some questions after this workshop, is there a good way to reach you? Do you have a preference, like LinkedIn? Yeah.
Yes, I'm very easily accessible on LinkedIn. You can find me on LinkedIn here or at the QR code.
Great, thank you. I guess I have another question. So,
yeah, this is great. Thanks for having me. Huh?
Yeah, no, this is a great presentation. If you go back to the architecture.
Yes.
I guess, yeah, sweet. So for the keyword index, you have doc1 keywords, doc2 keywords.
Yes.
Up to docn. So is that like, can each of those documents be kind of like a different type of unstructured data? For instance, could some be images, could some be text, et cetera, et cetera?
You mean like the document itself? The document itself could
like
be,
within that.
keywords have to be text. Like the document itself could be like images, and then like stored in the vector store, it could be like features of that image or something like that. But then you'd have to do some pretty advanced filtering to get the correct vectors to query the vector store with. The way that it works right now is that it's very easy to query the vector store because Llama Index is handling all of the vectorization for you. And so essentially what they're doing behind the scenes is they're using OpenAI to use all the vectors. So actually running this is like, unless you have free credits, is going to cost you like a few dollars, maybe, I don't know, maybe like $1 or $2. Yeah, so right now what's happening behind the scenes is all of vectorization is handled by Llama Index. if you're to do this yourself, if you want to have, a truly enterprise grade built out version of this, you'd have to design the architecture yourself without using Llama Index. And then, well, I mean, it's not that you can't use them, but like the customizability that most enterprises need would probably veer towards creating your own indexing strategies and your own and probably the ability to inject different vectorizations, because what you just asked for like makes a lot of sense. Like, yes, like you should be able to query multiple data types. And this is like a question that I get at talks like commonly is like, can I query structured and unstructured data? And so a lot of this stuff is like, yes, you can. You just have to go create that mechanism yourself. Yeah. As a practical matter.
Yeah, no, that makes sense.
Yeah. Thanks. Yeah. As a practical matter, if I have a stash of documents in various formats, PDF, links to Google Docs, what's the best way to ingest those into a vector store? For each type of document that you have, you're going to need a different vector embedding model. Unless you can, OCR your PDFs into text. If everything is like text, then you just need to turn it into text, and you can use the same embedding model. And then once you have the embeddings, make sure you save all the metadata with them. The name, the URL, if it's an S3 or whatever. The title, maybe the author if it's other people's blog posts, the date it was published, or the date you wrote it, or something like that. All the metadata that you need, and then you can store it into a vector database like Zillus or Milvus with a notebook. I I ran a notebook cell for about almost 10 hours, which is too long. You should not be doing that. But it's because I inserted a ton of data because I scraped towards data science, and yeah, you can just do it through a vector, a Python notebook. It's not that hard. In fact, I can send this one. What you want to do is you want to. Is this the right one? Yes. You want to store your data like this, basically. All you do is say like, hey, like I have, some batch it up somehow, and then say I have some inserts. Here's what, this is the embedding, and this is your embedding field. Here's your other like metadata that you want to, keep in there. I'll share this one. And then you just store it in there. And that's pretty much it. What is the differences and similarities between LangChain and Llama Index? So the way that I see them is that LangChain is typically used to operate with or on your large language model, and Llama Index is typically used to operate with or on your data. So Llama Index is very skewed towards retrieval, and LangChain is very skewed towards kind of like ops. Llama Index does use LangChain underneath, though. Cool. Any other questions? Oh, someone is typing. Okay.
I think I'm gonna go ahead and finish the recording, but thank you so much for that presentation, Yujian. It was awesome.
Cool. Thanks.